Hello everyone, I'm Tiantian Liu, a PhD student in Aalborg University. This time I'd like to present our short paper, Shortest Path Queries for Indoor Venues with Temporal Variations. With the development of indoor positioning technologies and the increasing availability of digital indoor maps, indoor location-based services are becoming increasingly popular. And shortest path or distance queries are fundamental in many indoor location-based services. For example, in an airport, someone may want to find the shortest path from his current position to the boarding gate. However, in real life, there are some temporal variations. For example, a door may be closed at a certain time. This kind of variations could change the indoor topology. In this work, we try to solve this kind of problem. However, there are some challenges to handle this kind of problem. The first challenge is the existing graphs used to model the indoor space do not consider temporal variations, which means they cannot be used to solve this problem. And another challenge is pre-computed door-to-door distances become invalid when this kind of variations happen. In this paper, we propose a new type of query called indoor temporal variation aware shortest path query. We design a graph structure that can capture indoor temporal variations. We also design two algorithms that check a door's accessibility synchronously and asynchronously, respectively. We conduct a lot of experiments to evaluate the proposed techniques. The results show that our methods are efficient. Okay, next, I will introduce some terms in this paper. The first one is ATI, active time interval, which means a door is open during this period. Here is an example. In this table, we can see door 1 is open from 5 o'clock to 23 o'clock. So from 5 o'clock to 23 o'clock, it's the ATI of D1. The next term is ITSPQ, indoor temporal variation aware shortest path query. Given a start point PS, a target point PT, and a current time step T, this query can return the valid shortest path from PS to PT. What is valid shortest path? That means it should meet two requirements. The first one is each door, DI in the path, should be open at T plus 30, where 30 is the walking time from PS to DI, and it is computed based on humans' average walking speed. Next, the path should not go through any private partition. In real life, there are some private partitions like offices. Usually, we do not go through this kind of rooms. We always go through some public rooms like hallways, stairs. So we take it into account in this paper. Let's run an example. In this figure, assume we want to find the shortest path from P3 to P4 at 9 o'clock. two paths can be considered. The first one is P3, door 15, door 16, then P4 with length 10 meters. Another one is P3, door 18, then P4 with length 12 meters. Apparently, the first one is shorter, but it goes through a private partition, so we do not consider it. It will return the second one. Another example is if we want to find the shortest path from P3 to P4 at 23:30, it will return null because door 18, door 15, door 16 are closed at that time. So this is our problem. To solve this problem, we propose a graph named the indoor temporal variation graph. It contains 4 paths. The first one is V, which is the site of vertices, and each vertex is an indoor partition. Next, E is the site of directed edges. Each edge is a door which can connect 2 partitions. Then LV is the site of vertex labels. Each label is a 3-tuple. ID is a partition's ID. P-type is a partition's type, which can be private partition or public partition. Then DM is distance matrix. There are some doors in a partition, and we store distances for each 2 doors. Then LE is the set of edge labels, and each label is also a 3-tuple. ID is a door's ID. D-type is a door's type, which can be private door or public door. ATI is active time interval, which I have introduced. Here is an example. The left part is a graph, and the right part is 2 tables. We use a partition table and a door table to store information of LV and LE. Then we propose some methods to process ITSPQ. Here is the overall architecture of algorithms. The overall framework is the Dijkstra-based algorithm. In this paper, we propose 2 methods to check. The first one is synchronous check. It looks up a door's ATIs and compare it to the arrival time when one just leaves for that door. Another way is asynchronous check. It directly refers to a time-dependent IT graph that only keeps all currently open doors. The information of IT graph only needs to be updated at the next checkpoint. We conduct a lot of experiments based on a 5-floor indoor space with 705 partitions and 1,120 doors. For temporal variations, we select random pairs of open time and close time to form the checkpoint site T in size of 4, 8, 12, or 16. The 8 is the default value. We use dirt S to T to denote the distance from PS to PT. For each citing of .s2t, we generate 5 pairs of PIs and PT to form the query instances. In each query instance, time t is fixed to 12 o'clock to make a file comparison. We run each query instance 10 times and measure the average running time and memory cost. Here are results. The first one is about the checkpoint site and search time, which we can see when the query time is fixed to 12 o'clock. Both two methods are insensitive to the checkpoint site. That's because in our citing, at 12 o'clock, nearly all doors are open. In such a case, adding more checkpoints to T has little impact on the graph topology at query time. Then we add a group of tests with T fixed to 8 o'clock. At this time, increasing checkpoint site T makes more doors be closed, reducing the cost of a graph search. As a result, the search of each method becomes faster. The second figure is about .s2t and search time, which we can see ITGS is always better than ITGA. The last two figures is about query time T. We test the search method's performance at different query times in a day. The search time of each method increases when T comes to 10 o'clock, and then stays stable when T is between 10 o'clock and 20 o'clock, then decreases when T is over 20 o'clock. In our citing, a large number of doors have been closed for the time before 10 o'clock or after 20 o'clock, and the corresponding IT graph becomes simpler due to the reduced temporal variations. On the contrary, the graph structure becomes more complex when more doors are open during the period from 10 o'clock to 20 o'clock. The same trend can be seen in the last figure, which is about memory cost. So that's all for this paper. Thanks for your attention. And if you have any questions, feel free to contact me. This is my email address. Thank you very much.